Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting paper. The title is ImageNet Worth One Video? Learning Strong Image Encoders from One Long Unlabeled Video. Now, that's very interesting title. The way the title is put up, I mean, the entire of ImageNet with millions of images, is it really worth just one video? Right? And what video are we talking about? How do you learn these strong image encoders? That's what we'll talk about in this video. Okay. This paper won an outstanding paper award at ICLR 2024. So let's get started. Let's understand what is this video that is being talked about. Okay. In fact, in this paper, the authors make this contribution of coming up with the walking tours dataset. So if you have been on a nice solo travel and if you've recorded your walks, then you understand what this is all about, right? So they basically took like 10 YouTube videos, and these videos are hours long, on average 1 hour 38 minutes long. They're just 10 videos. So it just literally contains 10 videos, right? And they're continuous egocentric 4K videos. Egocentric in the sense a single person just captured it in a single uninterrupted take. Um, and they are from urban scenes in different cities. They depict a large number of objects and actions with natural scene transitions. They're taken 4K, so high resolution, and 60 frames per second. The cities where they have been taken are as follows: Amsterdam, Bangkok, Chiang Mai, Istanbul, Kuala Lumpur, Singapore, Stockholm, Venice, Zurich. And also there is a wildlife safari video. So they're unlabeled, uncurated. There is no labeling of any sort on this on these 10 videos. Um, Now, since they are like egocentric videos taken by people like just walking on in these cities, these videos capture good variation, good continuous variation. So there are no sudden jumps in terms of lighting or pose or viewpoints, or relative object positions, occlusion. All of them are continuous in that sense. If there is background clutter, that's also continuous, and so on. Okay. So if you compare this walking tours, W tours dataset with other datasets, Epic Kitchen, ABA, or Movie ROM dataset, right? Here are some comparisons. So let's look at this first plot of lightness. So what they've observed is that if you look at x-axis is time and y-axis is lightness or lighting, brightness and so on. So what you observe is that the blue line is more or less pretty constant. Brightness doesn't really change. Lighting conditions don't keep changing frequently. While in other data sets, there could be like frequent fluctuations of lighting conditions. Objects per frame, if you look at y-axis objects per frame, W2s actually has higher number of objects per frame compared to many other data sets. If you also look at total number of classes, object classes, more of them are covered in W2s. Finally, if you look at the number of shots, well, W2s actually has very little number of shots compared to other data sets, all different cities, right? All of these subsets have very little number of shots, which basically means that there is a lot of continuity in the entire video, right? In the entire data set. So that's that. Now, so basically using these 10 videos, they want to train an interesting model, and they want to pre-train from scratch. Remember, they are not really training by taking pre-trained models and then doing some fine-tuning or whatever. They are trying to pre-train from scratch. Okay. Now, if you want to pre-train, you must have a pre-training recipe. You need a pre-training loss. So what is the pre-training loss that they want to use? In ImageNet, obviously, people used the cross entropy loss because you have like 1,000 different classes and you want to ensure that you predict the right class label. Here, what kind of a loss function do they use? So they use something called as a DoRA loss. Over the next few slides, I'm going to go into details about how this DoRA pre-training loss works and, how is it able to lead to very interesting model, right? So let's get started. The main motivation for them to use a different pre-training loss is this motivation. Today's models can actually learn from billions of images. But if you really think about it, if you think about a human watching these images, and if the human is like superhuman, and this guy really watches like 1 image per second, it will still take this superhuman 317 years to watch billion images, right? So clearly, it is not very efficient to train models with billion images. We should be able to train models with very little number of images, knowing that humans don't live for 317 years, and knowing that humans actually develop face recognition and color sensitivity abilities in 3 months, depth perception in 5 months, and visual acuity in 6 months. So something really super efficient about the way humans learn about images, right? So what they want to do is to really not learn from particular images, but learn from continuous videos. They want to learn by tracking objects. Okay, so they want to learn by tracking objects over different frames in these videos. So the main idea is that you take clips from these videos, particularly they take like a clip of 8 different frames from these videos, right? And they take several overlapping clips. So you can actually sample millions of clips from 1 hour, 38 minutes kind of a video, right? So they take several such clips, and then they find objects in the initial frame in every clip. And objects are found in the initial frame, and they're basically dragged across time in other frames in the clip. Okay. Now, this tracking is done using cross-attention maps, and we'll talk about how cross-attention maps basically help in tracking, but that's what we'll that's what we'll see. Okay. So when you're tracking objects, of course, in any frame, there could be several objects, but you want to ensure that you can track as many objects as you can. And you also want to have diversity in these objects. So basically, when you're tracking, you want to ensure that your track, especially when you're using cross attention, you want to ensure that these cross attentions are as disjoint as possible. So therefore, they use something called a synchron knob clustering of patch embeddings so as to enable this diversity. But obviously, this is a very, very high level discussion. We'll get into more details and also discuss about this architecture details on the right side as we go forward. Okay. So they leverage attention from, so basically, let's talk about the broad framework first on the right side. Right? So, there is a clip and it basically contains an initial frame and it contains multiple other frames. So maybe 8-frame video will contain the first initial frame and 7 other frames. Okay. They train their model as a student model derived from a teacher model. Student and teacher, both of them share the same architecture. It's basically a WIT architecture, vision transformer architecture. Okay. You take the last layer embeddings, CLS embeddings from the teacher. You see the CLS embeddings from the teacher, and you take the CLS embeddings from the student, and then define a loss function over those embeddings. Okay. Now, the student does not really get the same frames as it is, the input frames. The student basically gets some masked frames. Okay. So obviously, you're taking the CLS representation from teacher and the student, and you're trying to optimize some multi-object loss. We'll talk about some multi-object loss in detail. But the interesting part is the student doesn't take the frames as it is. The student basically takes some masked frames, where as you can see, some tiles or patches are masked, right? The masking is done using this multi-object mask, which is basically computed using a multi-object tracker. So the multi-object tracker is basically tracking objects across these frames, and it's basically obtaining these cross-attention multi-object masks based on the teacher's embeddings, as you can see here, right? And these masks are used to basically mask the inputs that are sent to the student, and then the CLS token representations from the student and the teacher are what are used for distillation, basically to minimize the multi-object loss. Okay. Now, obviously, we need to understand many things here, but this is the main architecture. The teacher is basically co-learned with the student in this architecture using this EMA. EMA stands for exponential moving average. So there is another pretraining loss which is popular called as Dino. So they take this EMA thing from Dino itself, where if the student has theta as the parameters, teacher has theta dash as the parameters. Of course, students' parameters are optimized using this loss. Teachers' parameters are not optimized using this loss, but they are optimized using EMA, or rather set using EMA, or updated using EMA, exponential moving average, such that theta dash just becomes alpha times the old teacher parameters plus 1 minus alpha times the new student parameters. Okay, so that's that. Now let's get into a little more details and try to understand, how these multi-object masks are computed, right? And that's what is explained in the picture below. Now, obviously, this picture we are going to discuss over a few slides, so we can look at it step by step. So to be able to do this, or rather, sort of, from this picture, it is sort of clear that you use the CLS token. So it uses the attention from the CLS token you use the CLS token to define the losses. But also what is interesting to know is that the CLS tokens, of different heads is basically what is used to compute these cross attention masks. And we'll see how this is done. Okay. So let's start with the very basics. So you remember, imagine that you have a video clip of T frames, and they use 8 frames as I mentioned. Okay. These frames have height and width and depth. Depth is 3 RGB, right? And then you take these frames and divide it into different patches. So H and W are the height and width, and let's have patch sizes P into P. So you end up with HW divided by P square patches per frame. Okay. But then what you do is to basically take these n different patches and pass them through a vision transformer model. And that basically gives you n different embeddings at the output plus 1 CLS embedding. So you also prepend a CLS token at the beginning. And that gives you n plus 1 different tokens at the output of the teacher as well as at the student. Okay. So ZCLS is the embedding vector representation for the CLS, and ZTLW the vector representation for the remaining n tokens, patch embeddings practically. Okay. So what do you do with this? So as you can see, what is done is essentially you take the second last layer from the teacher for the first frame. This is for the first frame. So you see, I mean, for computing the multi-object tracker, this module, you give the teacher representation for the first frame, and you also give the teacher representation for the teeth frame. I mean, whatever is your later frame in the clip. Okay. So you compute the standard QKV for these frames. I mean, it's you basically do linear projections, compute the QKV vectors for each of the positions. I mean, it's a 0th frame, but it also has like n positions and CLS token. You compute all of those. Okay. And you compute the attention values. So basically, and this is the second last layer. So you have that layer and you compute the attention values. You have the attention matrix for different heads. So in the particular width model, the vision transform model that they use has 6 different heads. That is why you see that there are A1 to A5, 6 different attention matrices, which define how much self-attention basically every patch has on every other patch. Okay. So you sample, you sample only I different heads. So out of 6, you can sample like 5 or 4 or 3 and so on, right? So these you only care about CLS attention. So let me basically take to the next slide and talk about that. So for the first frame, as I mentioned on the previous slide, for each head HI, you are going to compute the attention matrix AI, right? That's the attention matrix that you see, the 6 different attention matrices, and then you randomly select I different heads and get their CLS attention AI. So what does this mean? So let's say you basically chose, I heads in the sense I is a set. So K different heads. So the size of I is K. So if you basically get K different heads, then your AI is going to be K cross N because each of those, each of those, yeah, I mean, but so your KI is going to be K cross N because for each of those heads, you only take the CLS token and then you compute how much attention CLS token has with respect to every other head, So that is why AI is basically a K cross N matrix. Okay. So you take that K cross N matrix and you think about each head as representative of an object. So when you're selecting these K heads, right? In some ways, you're basically trying to figure out the attention or rather the percentage of an object in each of these patches. Okay, so the K cross N matrix is basically heads cross patches matrix. So think about it like this: if each head can be thought about as an object, each of those entries in the matrix, K cross N matrix, indicate how much a head is or how much an object is represented by any of those patches. Okay, so that's basically that. But that's just the weights for each of those patches. You want to actually get the object embeddings, and the way you get the object embeddings is by taking these attention weights, which are representative of what percent of that patch basically contains the object, and multiplied by the patch embedding, which is basically Q tilde. Okay, so what is Q tilde? Q tilde is the query vectors, and except for the CLS token, right? So that's basically that. And therefore Q tilde is basically n cross D. So you have AI, which is K cross N, and you have Q tilde n cross D, you get K cross D. So what you basically get is patch embeddings for these objects, K objects. Okay. So now you have patch embeddings for these key objects. And if you want to track these objects over time, what you can do is to basically compute cross attention by taking this matrix P, which is basically the query representation of the objects, and multiplying it with a key representation in the teeth frame. Remember, this query representation is only from the initial frame, right? And from the teeth frame, you basically get the key representation, and that's how you can sort of compute the cross attention. Okay. So it's also depicted in this picture here. So you basically do QK transpose, you get the attention matrix, you sample I different heads, or basically maybe call it K as well. I mean, I is the set, K is the size of the set. Okay. You take the CLS token. So that basically gives you Q tilde, and or other, that gives you that basically gives you AI, right? You multiply by Q tilde so as to get the prototype object prototypes or object embeddings in, so to say. Okay. Um, so what is being done here further? There's some more things which are being done here further. Okay, let's talk about why these are being done. Okay. So now key attention maps, you basically think about these maps to be spatial, representative of objects, as I said, right? So let's look at this picture. So you see in this picture, you have 5 different timestamps for this video. Initial timestamp, you basically try to figure out the objects and you track them over time. So when you track them, or rather t equal to 0 is not shown here, but you track them over time, you track them and you find that, well, these objects, basically when you try to represent them using these colors, you see that, they are representative of real world objects. So they are making sense, okay, when you visualize them. However, what you observe is that some objects like this building is represented by 2 colors. Now that's odd because, you have a yellow head and a green head, both of them capturing the same object. So the heads are supposed to represent disjoint objects, but they're not doing that job nicely. Okay. As you can see, some objects basically share colors, and that's not a good thing. Therefore, what they do is to basically somehow change these representations of these objects such that each object is represented by exactly one head. Okay. So as you can see, there are these blue and red and green kind of objects, and you can see they're real world different kinds of objects. Right. So how do they do this? So basically, the idea is that before I talk about how do they do this, the problem is that yes, you wanted your k different heads to be representative of k different objects, but it doesn't turn out to be so. K attention maps actually are overlapping spatially across multiple objects. It turns out one object can actually have 2 different colors, where each color represents a different, represents a different head. Okay. So how do you solve this problem? So the way to solve this problem is what is indicated in this part. Okay. So the way to solve this problem is to basically establish a correspondence between these object prototypes and patch tokens. I mean, that is what you want to obviously achieve, right? You want basically each of those object prototypes P, each of these object prototypes P, to be representative of one real world object and one real world patch as well, right? So therefore, what you want to do is to establish a one-to-one correspondence between these prototypes and patch tokens. And without getting into these details, what they do is to use some math called as synchron-NOP clustering. In simple words, it's basically some sort of a one-to-one matching in some ways while optimizing for similarities, right? So, and what they do overall is to basically, rather than having, these initial representations P, they come up with better prototypes P dash. Okay, so essentially they do a whole bunch of math here, in terms of using this SK kind of clustering method, so as to essentially get a transport matrix M star, right? And then finally, at the end of it, what they get is this P dash. And what is P dash? P dash is refined object prototypes. P dash is what is plotted in the third part here. Okay, they're the refined object prototypes compared to not so refined initial object prototypes shown here. Okay. Now, once you have these P dash, you have very clean object prototypes. Now, finally, what you want to do is to do cross attention. I mean, basically, they are your cross attention maps, right? So they are your cross attention masks, in that senses, you can compute cross attention, just like I showed here. So you can take P dash and multiply it with the keys for other timestamps, so as to essentially get these cross attention values. Okay. So it's actually shown more clearly here, right? So P dash multiplied by keys coming, P dash remember comes from the 0th time point, but these keys come from the teeth time point. You multiply them and you basically obtain these cross attention values. Okay. Now, these cross-attention values, after all, is a matrix K cross N because you have K different objects and you have N different patches. So therefore, you have K cross N cross-attention values. So what you do is to basically linearize it. So you linearize it, and then you sort of expand it to be linearize it, and you basically get those. Um, you essentially get patch by patch attention values, and you finally therefore convert it to a tensor TI, which is of the same size as the original you know for each of those patches. So remember, there are like K cross N, so there are K different patches. For each of those patches, ith patch, what you do is to linearize this n-sized stuff and make it like a P cross, make it like a square thing, and then you upsample it so as to make it of the size of the image, right? So once you upsample, make it the size of the image, you can actually do a Hadamard product of this TI with each of those values in X, the original frame matrix, so as to basically get a masked frame, right? Which is also actually shown very nicely here. You basically take this original frame and you mask it out by multiplying by these cross attention masks, right? Multiplying in the sense Hadamard multiply. Okay. Okay, so once you get that, you basically have your masked frames. Okay, so that's how these masked frames are obtained. Okay, in short. So what have we discussed so far? We've discussed that you take the input original frame, figure out objects, track them over time points via the teacher outputs, and these tracked cross-attention masks are what are used to obtain the masked frames that are input to the student. Now the remaining part is obvious. So you basically pass the masked frame to the student, unmasked frame to the teacher, take the CLS token from the last layer, and you compute the multi-object loss as follows. So what you do is basically this is the loss. So you take the CLS token from the teacher, theta dash is teacher, theta is student, and the xt u is basically the teeth time point frame, from the teacher, and XTV is the teeth time point frame from the student, but this is masked using OI. So you can basically mask for each of those heads separately. Okay. And it's sort of, student log teacher. So that's basically like a logit kind of the typical loss that you compute, right? So that's that. Now, obviously, you average it over all the heads, and you also average it over all different views. So what are views, right? So essentially, the point is that rather than using only one single frame, what you do is to basically project it out into 2 global frames and 6 local crops. Okay, so the way you do this is to basically take the original frame and then you crop it somewhere from 50 to 100%, and resize it to be of the same size as the original frame. And that's called a global crop. So, and again, this is popularly done in Dino. So, they obtain these global crops and local crops. But without getting into those technical details, which will make it more confusing, let me just say that you basically take a representation of this teacher frame and you compute, a CLS token for that, and you take the representation of the masked, teeth frame, and you get the CLS token for that, compute the multi-object loss. Okay. Now, as I mentioned, if you don't just do global crops, but also do local crops, and the local crops basically are done without any, so local crops are done for the student, global crops are done for the teacher. Okay. And when you do local crops, in the local crops, you do not do any masking, unlike the global crops where you do masking for the student. Okay. So in the local crops, again, you can compute the same multi-object loss, but without any masking. And then the overall loss is basically across all t different time points, you add up the global loss and the local losses. Okay. Specifically in their work, they use VITS with 16 cross 16 patches, 6 heads, and they use t equal to 8. So clips with 8 frames in that sense is where frames are sampled per second. Okay. That's that. So that's basically how DoRA is pre-trained. Okay, or that's how DoRA pre-training works. Now, how does DoRA with the walking tours dataset perform? So, well, to measure the performance, what they did was to pre-train their models from scratch. So they essentially, they did self-supervised pre-training, and essentially They do this pre-training. I mean, they do two types of pre-training using the Walking Tours Venice video and all the 10 videos. So they can just take Venice video and then just pre-train it using that. Versus they can also do LoRa pre-training using all the videos. Okay, so this is basically just the Venice video. This is all the videos. And these are other methods which can also be pre-trained. Like Dino is a popular method for pre-training, so that's the Dino method. And what you see here are the results obtained for using, for the three tasks: semantic segmentation, object detection, and instance segmentation. Okay. What do you observe? You obviously observe that DoRA performs better compared to other methods, um, like Dino as well. So where Dino has been pre-trained using the walk-in tools Venice dataset itself. Okay. But Dino could be pre-trained using ImageNet dataset also, right? And what you observe is that ImageNet pre-trained Dino performs worse compared to the DoRA model, which is pre-trained using just one video. And that is why the title that, hey, all of those ImageNet images are just worth one video. I mean, it just looks like that. Okay. I mean, the way the single video has been used for DoRA pre-training beats the way people basically use the categorical cross entropy loss for pre-training of Dino. I mean, and other laws. The Dino kind of pre-training using ImageNet images, millions of images, right? That's that. And that's true not just for semantic segmentation, it's also true for object detection accuracies. Um, in object detection, the map is slightly worse compared to Dino's ImageNet pre-trained one, but well, Dino's pre-training on WT Venice is worse than DoRA's pre-training on WT Venice. That's that. Okay. The results also hold when you look at other tasks like image classification and object discovery. So as you can observe, compared to other baselines, DoRA pre-trained with just WT Venice also gives you a reasonably high amount of gains, compared to any of the existing benchmarks, any of the existing benchmark methods. Okay. So what is also interesting is that DoRA is able to track objects really nicely. So you can observe that this guy, these guys in red are tracked even when they're occluded. So even when there is occlusion, still these objects are actually tracked really well. Even when this guy moves further in the frame, this guy with the green color is tracked very nicely. Okay. So that's it. That's it for this video. In summary, in this video, I talked about the walking tours dataset, which basically are 10 first-person videos taken by people touring a city, no cuts, high resolution, and hours long, right? On average, like 1.5 hours long kind of stuff. And then we also talked about this interesting DoRA pre-training loss, which does multi-object tracking across video clips. And in some ways, basically, they showed that one walking tour video, specifically the Venice one, becomes like a strong competitor to the ImageNet pre-training for several image and video tasks. I just talked about a few of those tasks here. The paper actually talks about more video tasks as well, like video, object detection, and segmentation for videos as well. Okay. That's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.